Okay, I apologize, but we are going to have a little discussion on continuity. And the reason I apologize is that this is going to take a few videos to do, just because I know I'll get long-winded otherwise, and I want to keep them a little bit shorter. So this first one, looking at this here, is talking about what it means for a function to be continuous. Now, remember, if we have, as you can see, this graph f here, and it just goes right through where the x value is c, we would definitely say that's a continuous function there. Why? Because from left to right, we go right through that point. The limit from the left, the limit from the right, they approach the same value, and that value is actually defined. So here's what we refer to as III of this process. A function by definition, f, is continuous at x value of c here, if and only if these three things happen. F of c is defined. If I put in c, do I get a value? Yes, I do. Gotta also have this one happening. What's the limit as x approaches c of the function? Remember, the left and the right approach the same value. That limit exists. Then III would be, what is the limit as x approaches c of f of x? Does it actually equal, does that limit that we just found in part 2 actually equal part I? So basically, is it defined? Is the value defined? C. Is the limit as x approaches that value existing? Yes. And then do those two equal each other? And if they do, then we can say something is continuous. So I'm going to put a snapshot of all of this on the Google Classroom for you so you can have it. But that's how we discuss, that's how we actually determine if a function is continuous. Now, if there is a discontinuity, okay, so let's say it's not continuous, all right, we want to describe what those discontinuities are. And there's two types. A removable discontinuity. So what if we had a hole in the graph? Okay, like we were moving along just like that last one, but that value, let's just say of c here, that was not existing there. Even though the limit did exist, the limit does exist, but the value's not there, then we call that a removable discontinuity or a hole. Non-removable can be two different types here. So if we have a discontinuity that's non-removable, that would be like the limit on the left and the limit on the right actually approach two different values. We could call that a break in the graph. And then the asymptote, obviously, if there's an asymptote there, either they both approach one down, one positive, infinity, one negative, or even the same way. That's an asymptote. We call that, by definition, non-removable. Okay, so what does this mean? Well, this is going to be what you are going to be asked to do. So I used my fancy stapler here to get these all in one sheet here for you. Couldn't find any tape. All right, so here we go. So when I'm going to ask you in my examples, I'm going to have you follow this procedure. Discuss the continuity of each function. Okay, so we're just going to give you a function. You have to first determine if there's any locations where the function is discontinuous. Okay, and at each discontinuity, determine if it is a removable or a non-removable discontinuity at that point. And then at each discontinuity, determine what the graphical attribute would be, a hole, break, or an asymptote. Okay, but here's the kicker, and this is where it gets tricky, and please watch the examples on the other videos. We must show the work that supports the conclusion. You can't just say it's discontinuous here. Even though some might seem obvious, the work is very important to us as we go through this, okay? So use the correct notation to label the components. So watch these examples very carefully, and I will follow this procedure.